The straight out definition for odd and even functions is written like this. Function is an even function if and only if when you take the argument and you use the additive inverse of the argument, it doesn't change the function at all. Now, when you do take the negative of the argument, what normally happens to a function? Right, it reflects over the y-axis. So what this says is a function is an even function if when you reflect it over the y-axis, nothing changed. And that would be symmetry about the y-axis. So that's the definition of an even function. Okay, well, let's talk about what the odd functions are. The odd function, a function is odd if and only if when you change the argument to a negative, it's the same as changing the entire function to a negative. What happens when you change the entire function? Right. So this means reflecting it this way doesn't change it from reflecting it this way. They're both the same. What it turns out is that that is symmetry around the origin. Let's just say that's a function. The question is, if I take the entire function and make it negative, is that going to be equal to making that negative? Well, what would that look like? That would look like this. A times negative x squared plus b times negative x plus c, is that equal to negative ax squared plus bx plus c? No, they're not equal at all. That's not odd. If all you do is memorize what happens with the graph, in other words, the fact that it is, right, if it is has 180 degrees symmetry around the origin, then it's an odd function. Then you have to graph everything in order to figure it out. But the definitions themselves are algebraic rather than graphic. And so for some equations, it's just easier to do it this way.
Can you draw it?
Can I draw it?
No, just like an odd function and an even.
Okay. Well, for an odd function, this would be an odd function because nothing changed. And this would be an even function. And then I turn it that way. It's the same function, same thing.